All right, I think we can probably start, and I will start introducing you. So please, ladies and gentlemen, again, it's Justin Hughes Jones. Who's Jones? So he's a Scala developer at Yoppworks who enjoys pure functional programming. I also want to tell that he's not only a Scala expert, he also has a nice repository related to A star. So it's a graph traversal and path search algorithm, as far as I get it. And it's written in C++ and for C++ and C#. And they say it's pretty popular, and he has a decent amount of stars on his GitHub repository. So please, Justin, let's give him a round of applause.
Thanks very much, Gregory. So first of all, I'd like to thank Ollie and all the organizers for putting together this really great conference. It's been really professionally organized in the background. So today we're going to talk about app. It's a single function in the Scala functional world. And we're going to get there via talking about three functions. We're going to go through map, flatMap, and then finally we'll look at app. So for each function, we're going to start by looking at the type signature. So the type signature tells us what the inputs and outputs are for the function. And you can see that map takes some type parameters, and one of them is the f parameter, which is a higher kinded type. So it has to be further specialized with another type. And then we have an a and a b. And the first parameter is a fa. So fa, we're going to think of it as being some kind of side effect or a computational effect. So it's a computation that yielded a value a if it succeeds. And what we mean by an effect is something that's not a pure function. So we could be talking about, like we'll see on this slide, we've got lists and options as side effects. The list is the side effect of dealing with multiple values. And option is the side effect of dealing with missing values. As well as that, you could say future's an effect. So anything that has some kind of side effect takes us out of the pure programming world. So the next parameter we got is f, which takes an a and returns a b. And that function is pure, so we expect it to be pure. It's not going to throw any errors. It's not going to deal with any side effects, right? So with the map function, we can take a higher kind of type like list, and we can apply a pure function to it. So this gives us a new list, and the new list is going to be of type f of b. So in this case, a and b are the same. They're both integers. We can map over an option, which means I want to run my pure function, and I want you to handle, maybe I don't have a value to apply it to. So in this case we do, so we just, we're able to turn it into a string. Now, if you have a map function, you can be a functor. So functors are something we took from Haskell. Haskell took it from mathematics, abstract algebra or category theory. So you don't need to worry about the name, but the reason we keep the name is because the word functor has a kind of precise meaning. So it tells us how the map function should behave for it to be a lawful functor. So throughout this talk, we'll be looking at implementations from the CATS functional programming library. So if you want to take your Scala into pure functional programming, you can pick up one of these libraries and start using these types in your programs without having to worry about all of the implementation details. So in the case of map, we've looked at the type signature, we've looked at what it does. So the other aspect is from what is the point of mapping things? So functor's power is it lets us reach inside an effect and apply a pure function. So in pure functional programming, we want to mostly write our code in pure functions because these are the ones that are easy to test. Because when we're reasoning about them, when we're testing them, when we're composing them, we don't have to think about all the side effects that can happen. But on the other hand, useful programs are built on side effects. So we really need the map function to reach inside the effect and apply the function for us. So the next function we'll look at is also probably familiar to most Scala programmers is flatMap. So flatMap also takes a higher kinded type f, which is going to represent our effect type. It takes another parameter, same as map, it takes a f of a. But you can see that the function it takes, f, is different. It takes a pure value and it returns an effectful value. And the return value is an effect of type b. So let's look at a real example. Let's say we have two functions and they both return futures because they're in the real world, so they have to deal with asynchronous behavior. It's something that's going to happen in some time. So we have to deal with nasty things like callbacks and errors and timeouts, and all of that behavior can be wrapped in the future. So the first thing we want to do is call getUser, which gets the future user, and then we want to get the account ID out of that user and pass it to getAccountStatus. So that's the second call, and what we'd want to do is compose these two functions together. But we can't do that because the types don't line up. We can't, when we get the FB from here, the future user, we can't pass that to AccountStatus. So what we could do is use Functor to do that. So we take the getUser call, we map it, which gives us the user, and then we call getAccountStatus. But the trouble is that map wraps its result into a future at the end. So what we end up with is the type future account status, which is not a type that we can deal with very easily. So what we could do is maybe flatten that. We can make a flatten function, but then we'd have to think about that when we're composing things. We'd always have to try and keep track of the nesting level and flatten things. So instead of that, we use the familiar flatMap function, which handles that flattening for us, which is why it's called flattening. That's why it's called flatMap, because it does the mapping and then a flattening. And that gives us the result we want. We can also use this syntax called a for comprehension, which makes the code look more imperative and it's easier to read. But it's essentially the same thing in the background. The compiler will do the same. It'll just make a map and a flat map. But what this syntax gives us is it makes it very clear that this is a sequence of instructions, and this one is dependent on this one. So when we write this code, if getUser was to fail, we don't call getAccountStatus because we couldn't, because we don't have the parameter we need. But even if we wanted to, this flatMap will short circuit. So as soon as it gets a failure, it will return a failure. So here we have another type class, monad. Monad's a structure we also get from Haskell in mathematics. And you can see that monad has the flat map, right? So if you implement flat map lawfully, then you can be a monad. But you also need the pure function. And the pure function, if you look at the type signature, all it does is it gives us an f of a for an a. And what that means is, when we're dealing with a monad, we can always take a pure value and pretend that it's in our effect, or we can lift it into our effect. So in cats, we can use this shorthand to call pure. So in this case, I'm saying I have a pure value that's a 1, and I would like it to be in a list. I'd like it to be in a list effect. So there we get it, which is shorthand for this. We have the list instance of monad, and we're calling pure on the pure value. So why is that useful? Because you can already make lists and you can already make options. It's useful because those two functions together in monad give us a kind of a small set of primitives that we can build other programs. So here's an example of that. We can prove that all monads are functors because we can write some code that implements the map function just using the monad interface. So this implementation of map, we specify that f has to be a monad. And that means that we can use flatMap and pure function on it. And then we can call flatMap on the FA, which gives us the A. And then what we would get here when we call FA is type B. So now we can use pure to lift it into the final result we want, which is FB. So you can see that it works. We can map a list. And instead of what flatMap would do, would just give us one list, but this gives us the the effect of mapping. So that's the two functions. Sorry, I should just say that what's the purpose of monads? So the purpose of monads is sequencing effects, right? So we're sequencing with short circuiting. So that's where they differ from functors. Okay, so here's the star of the talk, the app function. So I don't think commonly people use the app function a lot, but it's definitely there in most of the data types in cats. It's not in the standard library of Scala. But if you look at the type signature, then it's very similar to the other two map functions that we looked at. So we're still taking an f of a. And you can see that the function that we pass in is actually an effect, is also an in effect, right? So we somehow ended up in this situation where both our function and our parameter are effectful values. So here's an example of that. So we're using app for option. The very first case here is showing we can apply a function to an option. The function itself is an option. And if both the function and the parameter are some things, so they're not missing, then we can get the result. But for the other three cases, if either the function or the parameter are both missing, then we can get the correct missing value, which is none. So you can see that works, but it maybe isn't something that comes up day to day, that you maybe have a function, maybe you don't, or maybe it does, but not in my experience so far. Here's app for list. So app for list takes a function, it takes a list of functions, and then it applies that list of functions to the input parameter, which is also a list. So one thing I should just comment on, if we go back to the type signature, is there's only one f here. There's only one effect. So you have to be aware that the effect type is going to be the same for the function, for the input parameter, and the result. We never change the f's. Just like with map, just like with flatMap, we never go from a list to an option to a feature with these functions. We always stay within the same effect type. So app for lists gives us the power, if you ever find yourself with a list of functions, you can apply them to a list of values. But there's app instances for all kinds of monads, all kinds of data types. So reader, the reader monad, the state monad, future IOs IO, which are all ways of doing asynchronous and effectful things. So the question is, why? Why do we need app for all of these different types? It doesn't seem that useful. So to see why it is useful, let's look at another motivating example, right? So this slide is really setting us up for a real-world example for how we can use a function called MapTo. So MapTo can be implemented with with app. So first we'll talk about MapTo, and then we'll show how it relates to app. So in this example, I have a user data structure. This data structure represents a user account, and it has this information about whether my account is blocked. So this might be something like the FBI called the bank and said, block this account, or I would go to jail or something like that. So the bank needs to know that my account is blocked at the user level. And then I have an individual account, which has my balance. Now at the bottom of the slide, we have a pure function. So let's say we want to look at the user info, the account info, and then we have a lot of complicated business logic that tells us whether this account is in good standing or not. So the nice thing about this function is it's completely pure, so it makes it easier for us to develop it and test it and compose it with other functions and all that good stuff. So we want a way to apply the good standing function, but here we've got two effects. And the interesting thing about these effects is that they're completely independent, because each takes my email address, right? So I don't need to wait for get user to return before I call get account. Now the way of implementing these functions, these are using the cat's effect IO type. This is like future, but it's more functional. We don't really need to go into the details, but in this example, we're using that. This strange symbol means flatMap, but essentially it's a flatMap where we don't care what the result is. So what we're doing here is this dummy function is just going to wait 10 seconds, and then it's going to return some data. So this is just to give you an idea of what the code would do, right? So then we look at get account, which is the same, waits 10 seconds, and it returns this data. So here's how we would call that function. So we can call MapTo. Now monads have MapTo as well, but in this case we're using the applicative version of MapTo. And you can ignore the power part for now. Let's just imagine that these are all just IO. So MapTo takes, as its first two parameters, it takes two effects. And if those two effects yield successful values, so an A and a B, we can plug them into our pure function. So here at the end, we give it our pure function. So then we can run this code, and it will say, yeah, your account is good. Now, if you, let's just go back to the code 1 second. If you were to run this code without the parallel, just using regular IOs, this code would actually take 20 seconds to run. Because remember, with monads, and IO is a monad, we create this dependency, we create this sequence. So the implementation of MapTo for monads looks something like this. We're going to flat map the FA, gives us the pure A value. Then we're going to map that. And we've implicitly said these things are dependent on each other. So even though they're not, we have to wait. So we're going to wait 10 seconds for the first one, and then we're going to have to wait another 10 seconds for the second one. So instead of doing that, we can use the applicative instance, right? So let's just go back to the code one more time. So in this code, first of all, I explicitly said I want an applicative, and then I use the IO par, and then I wrap my IOs using this par function. So what that does is, in cats, you can use the parallel type wrapper to say, I want to use the applicative of this type. So IO has IO par. Essentially, it's the same type as IO, but its implementation is applicative rather than monadic. And then at the end of our code, we need to unwrap it using the unwrap function. So apart from that, it's just the same as using an IO. Okay, so the implementation of MapTo using the app function. Okay, so this is kind of a neat trick, I think. So what we're doing is we take our f of a as input, and because we're using applicative now, we don't have flatMap. We only have app and map. So then what we do is we map the commutation, which gives us the A, and then we can plug the A into the function here. But what we're also doing is we're going to curry this function with a new parameter of B. So what I'm saying here is, when you get a B, you can apply this function, A and B. And so the return value of this, now remember that map wraps things in an F. So once we've done this, what we get out is a function that turns B's into C's, and it's in the effect type F, which is exactly the signature we need to pass to app. So now we can call app with the FFB function and the parameter, and then we get the result that we want. So that's kind of that was kind of a eureka moment for me to understand that. So it means that the app function is not just used directly, it's also a very useful primitive for building interesting and powerful behaviors. So the app function lives in a type class called applicative, which also has the pure function, right? So the interesting thing about applicative is, unlike Functor and Monad, it doesn't come from category theory. It was it was more discovered by programmers. So they spotted some useful patterns where you could use this function, and then they built the applicative around it. So using this function to apply functions that are already lifted into an effect is called applicative programming. Applicative programming with effects. So just like we did with Monad, we can implement the map function with using just pure and app. So that tells us that applicatives are all functors. So all we need to do is lift the function that's passed to map using pure, and then we can use the app function. So map 2 is useful. How about map 3, map 4, map 5, and so on? So we can jump straight to map 5 and demonstrate how that's implemented. So you can see we have now five types to pass in, as well as the return type. We have an effect, we have a high-kinded type, and that f must be an applicative because we're going to use applicative functions on it. And then our function we pass in obviously has 5 parameters and returns a single pure value. And then what we're doing is we're going to use pure to lift a function, and then we just curry it 5 times, and then we can pass all the values in. And once we've done that, we get a lifted function that has the right signature, and then we just go app, and then we get the result, which is, you can see here is, it works. So a lot of people rave about traverse. Traverse is a very powerful function. You can see traverse in the Scala standard library, where you can use it to, say, turn a list of futures into a future list, which is a very common problem that comes up. And we can implement traverse using MapTo, and therefore we can implement it using app. So you can see here the input is a list of pure values of type A, and we need a high-kinded type G, which has an applicative instance. And what we can do here is recurse over that list and map to each successive head. We also have this function here that takes the pure values and turns them into something of the applicative type, of type B. Right, so this might seem quite abstract, but this is an implementation of traverse, which is really useful function. You can actually use traverse to do all kinds of things like mapping and filtering and more. So here's an example. We traverse a list of integers, and what we want back is a validated list, right? So we give it this list of integers, we give it a function, and we have a different rule for each kind of input number. So if the number is good, then we return a valid type. And if it's bad, then we return an invalid type. And this invalid null means it's an invalid non-empty list, right? So we're going to have a list of strings which are errors, and they're going to be in a list that can't be empty, because we can't have no errors. We can only have one or more errors. So when I call this on these numbers are all good. What I get back is I turn my list into a valid, and then the list of the valid numbers. Here's traverse with some invalid numbers. So here you can see that instead of getting a valid type out, we get an invalid type, and we get the non-empty list of all the errors. So what we've done is, instead of getting the short-circuiting behavior that we would have got with monadic application, is with applicative, we get all of the errors. So this is really useful. If you had to validate a large web form, for example, it means you can give all of the errors to the user right away, instead of waiting for them to fix the first one and then fix the next one and so on, doing a lot of unnecessary network transfers in the meantime. Just to go into a bit more detail on the validated class. So validated is very similar to either, and you'll find validated in the cats library. So the difference between validated and either is that it has applicative instance rather than monadic. So it represents a successful computation or an error or a failure of some kind. So for example, we can create a successful validated by using the valid syntax. And then what we're saying is, I have a valid 12, and here is the error type. And here's a failed validated. So we have, we create a non-empty list with a single error in it, and we set, and this is an invalid of type int. So in other words, if this wasn't a failed validated, it would have type int. So if you dig into the cat source code, you'll see app is implemented like this for validated. So essentially, if if both the left and the right side are true or valid, then we return valid and apply this function. If they're both invalid, then we actually combine them. And we know we can combine them because we have to have a semi-group, right? So a semi-group is kind of out of scope for this talk, but yikes, spoiler. So a semi-group is out of scope here, but if you have a semi-group, then you have a combined function. So you know how to join things together. So essentially, this means we already had an error, so we have two errors, so we want to join them together. If you just get one error on either side, then you just return the error. And that's what gives us the behavior that we can iterate over a list of things and get a list of validateds. So last year I did a talk on comonads, right? So comonads let you map over something, and it gives you the ability to look at the whole, to look at the thing from a wider perspective each time you apply the function, right? So that's a very short explanation for something that I did a 30-minute talk on. But all we need to know for the purposes of this talk is that we can do image processing with comonads. So here we take an image. I'm going to apply a filter to it. And then I'm going to flip it horizontally. So you can do both of those things with simple pure functions and the co-flatMap operation. So let's say that I have a pure function that can blend 2 pixels, and I have 2 images. So what I want to do is to be able to combine those 2 images, right? So the left image is just the original, the right image is the image mirrored horizontally. And because I have a applicative instance for focus grid, I can call MapTo on it and pass in the left and right images, and then pass in my blend function. So there we're using MapTo in something kind of visual. So to get that behavior, all I need to do is implement the applicative instance for my image structure. So I have an image structure called a focus grid, and you can see that the implementation of pure just wraps a pure value into an image with one element in it. But and then the app implementation is to map over the grid and give you the combined, apply the function at each step. So give you the combined images in our case. So the interesting what came out of that is the app implementation is actually very slow for this kind of data structure, because if you think about an image that's 2000 by 2000 pixels, that's 4 million operations. So your amount of operations really mount up quickly. So instead of implementing app, I used MapTo, and then I optimized that by using iterators, so I can iterate over my 2 effects. And I used a builder, so I can build up a new vector, which represents the pixels in the image. So by rewriting MapTo instead of using the default one, it's roughly 5 times faster. Now the original wasn't that slow, but being able to get a 5 times speed up is really useful. And you can do that because as long as you obey the rules of the the type signature and the laws of the types, you can go in and re-implement things however you want. So that's the end of the talk. So again, another thank you to the organizers. So some things you should read related to this talk. So we have the CATS documentation, which is really great. I've written a really long blog post about applicatives, which will actually go through this paper called Applicative Programming with Effects. And this is written in Haskell from 2008. So what I did was converted it into modern CATS and Zio code so that you can run it and see how it works. Another paper related to this is the essence of the iterator pattern. And one of these, the first paper also references this one, which is really good, called Do We Need Dependent Types?
All right, so thank you, Justin. Let's give Justin another round of applause.